All right, hello class. Um, Welcome back. I gave you guys 3 days to work on the final exam, so hopefully you're done with that and you can turn it in as soon as possible. Um, so let's see. For the next couple weeks, we'll be doing some some astrophysics. Uh, and then we may or may not have some extra time, so I'll think of something else to do, depending on how long it takes. Hey Jackson, hey Ben, hey Sofa. So I got my forge set up, and so for the past few days I've been forging, and I've been working on my knife. So this is my knife that I'm working on. It's quite thick if you look at it here. It's probably about 2.5 times as thick as a regular knife. So and it's about 11 inches long, I would say. That's a piece of paper. So probably it's going to get longer still, because when you hammer it to make it thinner, it extends, right? Because the volume is basically constant. So anyways, this was a railroad spike. So and the actual railroad spike was only about maybe this long. So the handle was actually the top of the railroad spike. So that's why it has that sort of shape. But should be done in the next 2 days, I would say, if I can get some time to forge. I am particularly happy though with the drop tip. So this is called a drop tip, when it's the back of the knife goes like this, and then it kind of goes to the tip. All right. So let's start some astrophysics. And so what I would like to do, so probably the fundamental problem in astrophysics is, how do you know how far away something is? Okay. If you look at a star at night, how do you know whether that star is a dim star that is very close, or is it a really bright star that's incredibly far away? Okay? We have no way of knowing just with our eyes, because you could have a dim star that's close and it appears bright, and then an incredibly luminous star that's far away, and it actually appears dimmer than the dim star that's up close. So sort of the two factors are intrinsic brightness and distance away. Hey Christian. So how do we separate those two things out? Okay, so today's lesson is going to be basically about how do we determine distances. So determining distances. And so what humans have done is we basically worked our way up to interstellar distances. The first thing we did is we just defined a unit of distance, right? We defined the meter, for example. Okay? And then we can use the meter to figure out how far away is the sun. Okay? So how have we figured out how far away the sun is? All right? So this is the first step in the astronomical distance ladder, okay? It's called the astronomical distance ladder. Okay, we figure out how far away things are that are relatively close to us, and then we use that to figure out how far away things are that are a little bit farther away, and then we figure out how far things are that are a little bit farther away. So we've been, throughout human history, we've been working our way out to greater and greater distances. Okay. So, how far away is the sun? How far away is the sun? Maybe I should turn this lamp off. So how do we determine that? And we've actually known this for a long time. I'm not solid on the history of it, but we've known how far away the sun is for quite a long time. Okay, so you might ask, how did they do it? So let's say that this is the surface of the Earth. Okay, and here's the sun. Okay, so for a person right here, for that person, it's noon. Okay, because the sun is directly up ahead. We would say the sun's at its zenith. The zenith is the highest point in the sky. Then maybe there's a person over here. Okay. And the sun is going to cast a shadow. Maybe I shouldn't. Maybe there's a person right here. Okay. And for this person, it might be the evening. Okay. And so the sun is casting a shadow. Okay. And the person measures the angle of that shadow. All right. And then there's a person over here who, here's the sun, it's shining down, and for them, it's the morning. And so that person measures the length of their shadow. Okay. So basically, what we can do is we can figure out what is this angle. Okay. So we figure out what is that angle by, well, I called it alpha, by looking at the shadows of two different people, one person in the morning and one person in the evening, at the same time. So you have to think about the sort of ingenuity of people, because this has been known for a long time. So they didn't have a telephone to call each other and say, measure your shadow now. Okay. So they had to figure out how to synchronize their measurements over great distances, because these people aren't 10 feet away. They're like, thousands of miles away. So how do you synchronize your measurement of the shadow? And so they were able to determine this angle. And then furthermore, they were able to figure out what this distance is, because they could just travel that distance. Okay. And then they knew that the Earth was a sphere, so they created this triangle here. So they know what this distance is. We'll call that distance D. Okay. And they were able to figure out, so basically they have this triangle here. They know this angle from the shadow measurements, and they know this distance. So they were able to do trigonometry and figure out what this leg of the triangle is and figure out how far away the sun is. Okay? So it's pretty cool. So basically they were using geometry to figure out how far away the sun is. And what they found is that the distance to the sun is around 1.5 times 10 to the 11th meters. Okay? 1.5 times 10 to the 11th meters. And this is called an astronomical unit. Okay? Which is also known as the AU. So this is defined as 1 AU. Of course, the Earth's orbit is an ellipse. It's not a perfect circle. And so that distance is changing slightly. So this is defined as the average distance between the sun and the Earth. Okay. So yeah, that's pretty cool. That's how they did that. The astronomical unit is a great way of measuring distance within a stellar system. So it's great for between planets, the size of a solar system. Those distances are all most appropriately measured in AU. For example, for example, you could have the Mercury is about a third of an AU away from the sun. Venus is about 2/3 of an AU away from the sun. Earth is 1 AU away. I believe Mars is like 1.5 AU. Jupiter, I think, is maybe 8 AU, 5 AU, something like that. Neptune, the planet that's farthest away, is something like 30 AU. So the diameter of the solar system is right around 60 to 70 AU. Okay. So another unit of distance that is useful in astrophysics is the light year. So 1 light year, okay, is equal to the distance that light travels in a year. One Earth year. Okay. And there are all kinds of little, qualifications and things like that. For example, this is the speed of light through a vacuum, that sort of thing. So anyways, we can calculate it. So first of all, we need to put it, we know that the speed of light is 3 times 10 to the 8th meters per second. So what is 1 year in seconds? Well, 1 day is 86,400 seconds times 365 for the number of days in a year. 86,400 times 365. So 1 year is about 3.15 times 10 to the 7th seconds. Okay. So I multiply that by 3.15 times 10 to the 7th seconds. So this is rate times time equals distance. And we get that 1 AU is about 9.5 times 10 to the 15th meters. Okay. Just as I like to remember a light year, just it's a useful thing. I usually remember it as just 10 to the 16th meters. Okay. So think about how big a light year is away compared to an AU. An AU is 10 to the 11th meters. A light year is 10 to the 16th. So that's a factor of 10 to the 5th between them. That's 10,000. And think about this. The closest star to us is around 4 light years away. Okay, so it's about, to get to the next star system, it's about 40,000 times. Oh, excuse me, 100,000. 10 to the fifth is 100,000. So it's 400,000 times the distance from the Earth to the Sun, to the closest star. Let's see, we got some people here. Hey, how was the AP exam? I'm curious. All right, so that's 1 light year, which is abbreviated LYR. So we have that. We've got 1 AU. Okay. And there's another common unit of astronomical distance, which is called the parsec. And 1 parsec is about 3.3 light years. Okay, so this is just a definition. This is just a definition. All right, but the AU is defined was defined by this sort of measurement. Okay, so how do we figure out how far away other stars are? Turns out we use the exact same methodology. Okay, and this method is called the parallax method. Okay, and this method works. It works for nearby stars. And when I say nearby, I mean in the relative sense, because even the closest star to us, the Sun, is 10 to the 11th meters away, and the next closest one is 4 light years away. So this method works out to roughly 1,000 light years, I believe. Maybe it's a couple hundred, but okay. So it works for stars that are within our own galaxy, certainly. You can't use this method to determine how far away a star is outside of our galaxy, or even for stars that are on the other side of the galaxy. Okay, the galaxy is really large. The galaxy is around 15,000 light years across. So we can only see a small or find distances within a small part of our galaxy using this method. Okay, so here's what we do. Here's the solar system. So here's the solar system, here's the Sun, and here's the Earth in its orbit. Okay. Actually, before we do this, let me tell you the idea that this is based on, and I want you to actually try this. Put your thumb out in front of your face like this, okay? And I want you to hold it so that you're looking at something off in the distance. So you're looking at something in the distance, but your thumb is in the way, okay? And then I want you to move your head back and forth like this. Like you're saying, oh, no, you didn't, something like that, okay? And what you'll notice is that if you move your head back and forth, your thumb appears to move against the background. That's called parallax, okay? Okay? So your thumb, you move your head, your thumb moves against the background. So if this is the Sun, And this is another star. Okay. All right. And then there are these background stars. Okay. So if this is the Earth, maybe this is the Earth in winter. Okay. You can see that the star you're interested in is at a certain spot against the background. And when I say background, I mean stars that are really far away. Okay. Okay. And then the Earth is orbiting around the sun, so eventually the Earth is going to come over here in summer, and you can see that the star appears to have moved. Okay, the star was during the winter was in front of this part of the background, but now because the Earth has swung over to the other side, now it's in front of some different stars in the background. Okay. And so so the star didn't actually move. It's just that the Earth did, which changed our perspective slightly. Okay? So based on that, we can figure out, okay, what this angle is. This angle is called P, the parallax angle. Okay? And this distance right here, D, is how far away the star is. Okay? And this is a right triangle, by the way. And this distance is the distance between the Earth and the Sun, which is 1 AU. All right? And we can see that just based on simple trigonometry, that the tangent of P, now P is called the parallax angle. Okay? The tangent of P is opposite over D, the distance to the star. So that says that the distance to the star is 1.5 times 10 to the 11th meters over the tangent of the parallax angle. Okay? So notice how in order to figure out the distance to a star, we had to know what 1 AU was. Okay? So you see how this method of determining distance relies on knowing the distance to the sun. Okay? So it actually turns out that the next method of measuring distances is going to rely on the parallax method. So basically we use a method that lets us see stars that are close by, allows us to determine distances to stars that are even further away. All right. One thing about parallax angles, I'm going to define some different things. So there's something called 1 arc minute. So an arc minute is equal to 1/60th of a degree. And then there's an arc second, which has which is 1/60th of an arc minute, so it's 1/3600th of a degree. All right, and it actually turns out, going back to the parsec, if the parsec is defined as 3.3 light years away is something that has a parallax angle of 1 arcsecond. Okay, so that's why it's called the parsec. It's parallax of an arc second. Parsec. Um, so it's a portmanteau. Let's just do a basic calculation. So what you'll see is that, okay, so let's just do an example. How far away is a star? With a parallax angle equal to 0.75 arc seconds. AS is the abbreviation for arc second. MAS is milli arc seconds, so that would be thousandths of an arc second. So you could say this is 750 milli arc seconds. And I want it to be in light years. Okay. So let's convert this to degrees. Okay. So this means that P equals 0.75 arc seconds, but we know that there are 3,600 arc seconds in 1 degree. So the arcs, so 0.75 divided by 3,600 is 2.08 times 10 to the minus 4 degrees. Now I use this formula, D equals 1.5 times 10 to the 11th meters over the tangent of 2.08 times 10 to the minus 4. And we get 4.1 times 10 to the 16th meters. Okay? Now, remember, 1 light year is approximately 10 to the 16th meters. So this is roughly 4.1 light years away. All right? Notice how this is as far away as the closest extrasolar star to us. Alpha Centauri is about 4 light years away. So even the closest stars have parallax angles that are fractions of a degree. Okay? And this is the limiting factor of the parallax method. Okay? Is that, all right? It's just really hard to measure these minute angular differences. This is the limiting factor in the parallax method. All right, so that's my lesson for today. I hope that was entertaining and thought-provoking. And I will talk to you tomorrow, where we'll determine the next step in the cosmic distance ladder. Okay, bye now.